Okay, good evening. Welcome to the session. Today we are talking about the material balance with chemical reactions as well as combustion calculations. So a good questionnaire also has come, so that please participate in this live lectures so that we can clear all the doubts. And please kindly watch my videos 1 or 2 times. I am explaining excellently well, and all the steps I am explaining you properly. But still, if you have any doubts, like, you can ask me that. Okay. So yesterday the highlights of yesterday's one is the excess oxygen what we give only for the theoretical equation. Okay, that is the fundamental thing what you have to keep in your mind. Let us say they say that 98% combustion has happened. Okay, after that 98% combustion has happened, but the oxygen will be supplied only for 100% combustion. Okay, later 98% combustion is only for that particular component. Okay, so here don't take the oxygen for the 98% combustion and all, and calculate what is the total one, because that's what I told you, that in earlier we don't know what is the combustion. We assume it should be 100. Okay, so yesterday I told you that if you take some coal and you want to burn it, so you never anticipate that 98% or 96%. So you anticipate 100% combustion and then provide an extra facility for that. We call it as a facility, means to extra oxygen or extra air is supplied such that 100% combustion is happening. And after getting the flue gases from the ORISAT instrument, we can analyze that how much combustion has happened. So after that only we can say that it is 98% combustion or 95% combustion. Okay, like that. So please, while calculating the excess oxygen, you have to calculate for 100% combustion. This is the main important point in the combustion. Rest of all things is very simple. Okay, right. So today let us start with recycle, bypass, recycle and purge. Bypass, recycle and bypass, recycle and purge. So this is the general thing what we'll calculate in the industry. If you go to any industry, there will be pipelines will be passing from here and there and all. So in order to save some or not save, in order to improve, let us say, in order to improve the quality, the recycle will be done. Okay, so the recycle means the product stream. So some ratio of the product stream is sent back to the feed. That is called recycle. But while recycling, there is a chance that more number of inerts may enter, because the feed will be directly entering, we'll be getting the products, and with the total products we are not taking, some of the ratio from the product stream we are taking it out and adding to the feed, such that whatever the inerts are there, that inerts will be passing through it, because most of the things is a chemical reactions which will happening there, and we'll calculate that. Even if it is some of the oxygen related reactions are there, because oxygen we cannot directly send it, we have to send through the air. So air will have argons or nitrogen or something else. So we take that particular inerts, and that inerts, generally argons is the inerts, so that inerts will decrease the reaction rate. Okay, for that some purge is being done. The purging will be done only from the recycle stream. The recycle stream is taken from the product stream. Okay, and it is being sent to the feed stream. From this recycle stream, some purge stream, some stream we take it out, so that we want to reduce the inert content which is present in it. Okay, so that is called as a recycle. Well, if you come to the recycle and purge, if you come to the bypass, then most of the evaporators will go for the bypass. Why? Because if you concentrate it, if you want to concentrate it, we will evaporate the water. Okay, that is the tie materials and all we discussed about it. So it will just evaporate it, and then a high concentration may be there, but you may require some less concentration. Okay, so that less concentration, what you do is you have to send through, from the feed, you have to add to the product. So that is called as a bypass. Bypass means bypassing from the feed and adding to the product stream. So that what will happen? The feed stream is a diluted stream, product stream is the concentrated stream. Suppose if you take some of the feed stream and add into the product stream, that will get somewhat diluted, and he will be asking the questions that what should be the bypass ratio such that the final product content will be the tie materials percentage will be something like. So these type of questions or these type of things will be there, and in industry most of the things they use these type of things. Okay, so you have to have a lot of practice on this, and I'll give you a tips here how to calculate the material balance and how to get the recycle ratios, how to get the bypass and all. Okay, so if you have any doubts, please you can put questions on it. So recycle stream. First we will discuss about the recycle stream. Recycle stream and purge, both the things we can read at once. Recycle stream and purge. So here you have a mixture. Okay, not mixture. M means mixer. Mixer. Okay, so mixer. Then you have a process. You have a process. Then feed. Okay, fresh feed. So the fresh feed is being sent to the mixer, and through the mixer it will go to the process. Process generally will be a reactor or the condenser, depends upon the conditions here. Process, and this is the process product. This is the process product. So this is called as a mixed feed. After it is passing through the mixture, it's called the mixed feed, and after processing it is called as a process product, and S means separator. S means a separator. Why? Because I told you that for the recycle we'll take some part from the product. We'll take some part from the product, and this is nothing but your final product. Okay, this is your final product. So what is the process product which has come? That has been divided into two parts, not equal always. Okay, with some ratios they may do it. So, and then what they do is they will add to the mixture. So this is called as recycle stream, and it is termed as R. Recycle stream, and is termed as R. Okay, so this is the process feed, and then now you can understand what is the mixer is. Feed plus recycle stream will give the mixed feed. The mixed feed will go into the process, and it is reacted, and the process products will come, and some products will be taking, some ratio will be taking back and putting into the or mixing to the feed. This is called as recycle stream. Please remember, from the finished product. Okay, from the finished product, some part of thing is taken back and added to the feed. It's called recycle. So what is purge? Purge is this. Purge is this. Some stream is taken from the recycle stream. So that purge stream is that. Okay. So this is called as a recycle stream. And what are the advantages of this recycle? The advantages of recycle is to increase the yield. To increase the yield. To increase the yield. To increase the yield. That is the advantages to increase the yield. So yesterday we talked about what is the yield and all. Okay. So this is called as a recycle, and this is now. Let us come to bypass. Let us come to bypass now. What do you understand by bypass? So I told you that opposite this separator will be there here. The separator will be there here. So what is the process feed is there? What is the process feed is there? That is sent to the separator, and some part is taken here. Some part is been taken there from the separator. Okay. And then after the separator, some part of the stream will go into the process. And after that, it will be the process. The bypass stream will be added to the process products to get final product. So here we can have a mixer. Here you can have a mixer. Here you can have a mixer. So this is called as bypass. So arrows, you can understand the arrows. Because the flow sheet requires an arrows. Okay. So this is arrow, and this is an arrow, like this. So this is called as the bypass. So what are the advantages of bypass? The advantage of a bypass is, to get the required composition. I told you that while doing the evaporation, generally evaporators will go for this. Generally, that's what I told you. In the evaporators, we cannot have our own composition. So what we do is, whatever the best we can do, we do in the evaporator, and then we will mix. We'll send to the mixer. From the process feed stream, some stream will be taken it out and added. So this is called as bypass. This is called as bypass. From the feed, some part is being bypassed, and then directly it is being added to the finished product, that is process product, and to get the final product composition. Okay, so this is the theory about the recycle products. So here let us have some practice problems on this, and then we'll go for the gate problems. Go for the gate problems. So limestone this one is an excellent one. The limestone or let us do this. Yeah, we will do this problem, so it will be easy for you to understand. Because nitrogen hydrogen mixture with a molar ratio of 1:3 is used to manufacture for the manufacture of NH3, where 18% conversion is achieved. After separating NH3 from product, the unconverted gases are recycled. The feed contains 0.2 moles of argon per 100 moles of N2H2 mixture. The toleration limit of argon entering the reactor is 6 parts to 100 parts. N2H2 mixture by volume. Calculate A, the fraction of recycle that must be continuously purged. B, the overall yield of ammonia. yield of ammonia. The overall yield of ammonia. Okay. So here, it's a very, very interesting problem statement here. Nitrogen, practice. Nitrogen-hydrogen mixture with a molar ratio of 1:3 is used for the manufacture of ammonia, where 18% conversion is achieved. After separating NH3 from product, the unconverted gases are recycled. The feed contains 0.2 moles of argon per 100 moles of N2H2 mixture. The toleration limit of argon entering the reactor is 6 parts to 100 parts N2H2 mixture by volume. Calculate the fraction of recycle that must be continuously purged. The overall yield of ammonia. So, as he has not given the flow sheet, we have to draw the flow sheet here. So, what is the flow sheet? What he says, it is a recycle problem, correct? So, a reactor will be there, and then we have a feed and we have a mixture M. We have a mixture M and we have a feed. Okay, through the mixture, after the reaction is being done, we are only 18% of ammonia is coming, and rest of all 82% unconvertible gases are going out. So, to get that particular ammonia, we require a condenser, so that whatever the 18% of conversion has happened and whatever the ammonia has been produced there, that ammonia we can take it out with the help of the condenser, and rest of all the gases is sent to the is left out. The toleration limit for entering the reactor is 6 parts to 100 parts. So that is only the toleration limit, because as the feed is continuously coming in, the argon, if it is developed more, so even 18% of conversion will not be possible. Okay, so this condenser is used to take out the liquid ammonia out. So here we can say that no ammonia will be present here. Okay, so entire liquid ammonia is coming out here. Okay, so let us write down here what is the feed content. So let us say what is the okay. So let x kgs the kg mole. Let's x kg the kg mole of N2H2 mixture recycled, and let y kgs let x be the kg moles of the recycled stream and y be the kg moles of N2H2 mixture in purge stream or purged. Okay, so let us say that, so what you have seen, x kgs be the recycled back. So at what is the mixture content here? So amount of N2 plus H2 mixture, amount of N2 plus H2 mixture entering the reactor is 100 plus X moles. Okay, so like this we have to write. So let amount of N2H2 mixture entering the reactor is 100 plus X moles. Okay, 100 plus X moles. 100 means the feed, you can take it as 100. So 100 plus X, 100 plus X is what entering into the reactor. So amount of N2 plus H2 mixture leaving the reactor here, leaving the reactor, how much? Leaving the reactor is 0.82 of 100 plus X moles. 0.82 plus 100 X moles. Leaving the reactor and condenser, let us say, and condenser also. Amount of NH2 mixture leaving the reactor or leaving the condenser, that is the best part. Leaving the condenser. Leaving the condenser is 0.82 because total ammonia is coming out here. So whatever it is going in here, it is 0.82, 100 plus X. And rest of all, which has come here, is 18% of that. Okay, so amount of N2H2 mixture leaving the condenser, we'll write like that, is 0.82 moles. Now, what is argon? What is argon in feed? The argon in feed is 0.2 moles. The argon in the feed is 0.2 moles. So he has given 100 moles of N2H2 mixture. So in 100 moles of N2H2 mixture, we have 0.2 moles. Then argon entering the reactor. Argon entering the reactor means when it enters the reactor, after the recycle enters here. But what is the toleration limit? The toleration limit is 6 parts to 100 parts. Only that content has to enter into the reactor. So argon entering into the reactor should be how much? 6 by 100 into 6 kg moles. Only this part has to enter. So argon leaving the reactor. Argon leaving the reactor. Same thing, because argon doesn't react with anything. So it is 6 by 100, 100 plus X kg moles. Okay. Please practice this so that you'll get an idea about it. So argon leaving the reactor. So moles of argon by moles of N2 plus H2 mixture. N2 plus H2 mixture is 0.06 100 plus X by 0.82 100 plus X is equal to 0.073. This is the ratio of moles of argon by moles of N2H2 mixture, 0.73. So in purge, moles of argon, moles of argon is 0.073 Y. So in purge, moles of argon is 0.073 Y. So for steady state operation, the argon entering is equal to argon leaving, correct? Argon entering is leaving. So how much it is? 0.073 Y is equal to 0.2. Because whatever it is entering, we are leaving it out. So that only 0.2 moles will be circulated. So 0.7 Y is equal to 0.2. Then Y is equal to 0.2 by 0.073. So that will give you 2.739 moles of N2H2 mixture. So this much of total mixture which is coming out has to be purged out. So N2 plus H2 mixture, I'll just draw a line here. So N2 plus H2 mixture in recycle stream is nothing but 0.82 100 plus X is equal to X plus Y. And if you solve for X, okay, so 100 plus X is equal to X plus 2.739. So here X is 440.338 moles. 440.338 moles, and the fraction of recycle purged is Y by X is equal to 2.739 by 440. So that is nothing but 0.00622, and yield of ammonia, what is yield of ammonia? 0.18 into 0.18 by 2, 100 plus X. So this will give you 48.6304. So this is the classical problem. Just go through the procedures, how we have solved this, so that, and there is no a proper calculation procedure for the recycle. It is up to the author. Okay, if you see different books, or if you have ideas, you can have your own calculations. Okay, so I got this idea, so we have solved like this, and you may get some idea here, and you can do that. So there is no hard and fast rule that you have to follow the same procedure, but this procedure will help you to understand what exactly we are doing here, so that you can get an idea how to calculate the purge and recycle ratios. Okay, so this is the wonderful problem. If you practice it, if you go on practicing it, you will be definitely will get the idea. So another super problem we will solve here. That's what I am telling you. So it is not compulsory that you have to use my method here, but you practice with this method. If you get any other idea to calculate much faster, you can do that. Okay. So if you practice the problems, so gate problems will be very, very simple. Okay. So another problem is limestone. (95%) limestone containing 95% weight CaCO3 and 5% SiO2. 5% SiO2 is being calcined as shown in the flow sheet below. Heat for reaction is supplied. Heat for the reaction is supplied from a furnace. Burning powdered coke, which is essentially pure carbon. So here furnace, air, coke, clean, there is a recycle, this is the clean gas, this is Z, and this is recycle. See, the hot flue gas analysis, the hot flue gas analysis, 5 mole percent CO2. The clean gas is found to contain 8.65% CO2. In order to conserve some of the sensible heat, a portion of the clean gas is continuously recycled, and mixed and mixed with fresh hot flue gases after mixing the gas entering the clean analyzes mole percent CO2. A. Calculate kg of crude CaO produced per kg of coke burnt. B. Calculate the recycle ratio. Okay. So these are all practice problems. Okay. This much of big problems, it won't come in the gate. Okay. But if you do these problems, that problems will be very simple. That's why I am giving you a thought process problems. Okay. In this type of problems, you can reach to the solution as fast as you can. I think I get some ideas and solve this problem. While after practicing, you may get some ideas. Okay. So, but the final answer should tally. That is answer. That is the step. So, what steps you take, that is one. But I have the practice, because after doing so much of experience, having experience and so much of thinking about this particular problem, I am solving like this. Okay. So, calculate the recycle ratio. Now, the solution. Limestone containing 95% weight CO3 and 5% SiO2 is being calcined as shown in the flow sheet below. Heat for reaction is supplied from a furnace burning powdered coke, which is essentially purely carbon. Okay, the hot flue gas analysis, 5 mole percent of CO2. The hot flue gas analysis, 5 mole percent CO2. The clean gas is to contain 8.65% CO2. Okay, 8.65% CO2. In order to conserve some of the sensible heat, a portion of the clean gas is continuously recycled and mixed with the fresh hot flue gases. After mixing, the gas entering the clean analyzes 7 mole percent CO2. So now you have to see here what is the process which is entering here. So I identify the streams here. So I take this as point A as a mixer, and I take this X. Okay. So the hot flue gas analysis, 5 mole percent CO2. So here it is 0.05. That much of CO2 which is entering into the clean. But it is after mixing it is become 0.07. After mixing, it has become 0.07 CO2 and entering into the clean. Okay, because he has said continuous, after mixing, the gas entering the clean analyzes 7 mole percent. So after mixing. Okay, so the clean gas is found to contain 8.65 CO2. So the stream which is coming here will have the 8.65, so CO2 which is coming out. Okay, so how to start the problem? So we have identified very clearly here. See here it is very clear. In the clean limestone is coming out. So limestone is introduced. Limestone has, suppose 100 kgs of 100 weight. Okay, 100 kgs, let us say 100 kgs of limestone which is coming out. Out of that 95 kgs is CaCO3 and 5 kgs is SiO2, silica. Kgs it is there. Okay, should be careful here. If everything is given in kgs, no. Some percentage is given in moles. So we have to convert that into moles. You should be careful. So have you identified? So I identified X kgs here, which is entering, and I have taken the Y kg coming in which we have 0.865 fraction. Amount of CO2 which is coming out of the clean gas is 0.0865 Y. Okay, are you clear now? Now let us start here. Solution. 100 kgs of limestone. 100 kgs of limestone. If 100 kgs of limestone is there, then CaCO3 gives CaO plus CO2. Correct? So here what is happening here is we are using the coke. We are using the coke and air to condition this. Thereby the hot flue gas is being generated. This hot flue gas is sent to the kiln so that this, with the help of this gas, the limestone will get burnt. Okay, so that is what happening in the kiln. After burning it, we are getting some CaO plus CO2. Because it is an endothermic reaction, we have to provide the heat. So it will convert into calcium oxide and carbon dioxide. So now, but the amount, whatever the amount is given, so moles of CaCO3, how much is the weight? Is 98. We have already written here 95 kgs. 95. What is the molecular weight of CaCO3? Molar mass 100. Molar mass is 100. Okay, molar mass is 100. Don't think that I have just divided by 100 here. No, which is the molar mass. Weight by molar mass will give you the molecular weight. Okay, so how much you get? 0.95 kg moles. 0.95 kg moles. Similarly, you convert the moles of CO2. Okay, moles of CO2. From here, 1 mole to 1 mole. So moles of CO2 is 0.95 kg moles. Okay, so this is what the reaction and all has happened here. Okay, number of moles of CO2 and moles of CaO also, 1 mole to 1 mole, so 0.95 kg moles. So from the reaction we have written this kg moles which has been generated here. Okay, so we'll just take 5 minutes break and then I'll join you.